Alright guys, this is Mr. Parham. We're going to go ahead and do our second lesson in Module 1. And so today we're going to talk about the next set of discoveries in our exploration of the history of the atom. So that's what we've got on our slate today. What I want you to do is go ahead and put your phones away and complete the bell ringer in Canvas if you haven't already done so. So if you haven't, go ahead and pause the video and knock out the bell ringer. Come back whenever you're finished. Okay. Number 2, go ahead and join the presentation by going to that website, joinpd.com, and using the code here at the top right. That's GRZXUK. I know it looks like there's a space in there, but just type in the code without the space, and it'll put you right in there. Okay. So take a second to do that. That's a mandatory step. That just makes it so that I can monitor your progress as you go through the lesson and give you feedback on any responses that you give me. All right, and then number 3, go ahead and get out paper and pencil so that you can write down notes, ask any questions that you might have, or write down any questions that you might have for later. And then in this section, there's not really any example problems, but still, the more you write things down, the more likely you are to remember them later. Okay, so go ahead and do those things. And I'm going to move my face over so that I can click the arrows. Alrighty. So we are still in Module 1, still talking about the atom. And today we're going over section 1.2, which is defining the atom. So yesterday's lesson we talked about early ideas. Who came up with the first idea of the atom, and then how much time passed before it was able to be expanded upon. And we talked about like Democritus and John Dalton and his atomic theory. Okay, so if you forgot that, go ahead and go back and review those notes from yesterday. All right. Our objectives for today, we want to be able to do 3 things. We want to describe the progression of the history of the formation of the atomic model. Yesterday we did Democritus and John Dalton, and today we want to go from John Dalton to present day. All right, so we want to be able to describe that history there. Number 2, differentiate between the subatomic particles known at the time of each model. So remember when we left off yesterday, Democritus and John Dalton thought atoms were indivisible and indestructible. They didn't know that atoms were made up of little tiny particles called protons, neutrons, and electrons. So whenever you talk about John Dalton's model, you need to know that John Dalton thought it was just a solid sphere with nothing inside of it. And then same with the other people's models that we're going to talk about today. What did they know at the time that they discovered their models? And then the third objective is to identify subatomic particles in terms of mass, their location in the atom, and the charge that they carry. Okay, those are our 3 objectives for today. And then review vocab, we're going to talk about what a model is. So a model, just remember, is a visual, verbal, and or a mathematical explanation of data collected from many experiments. So visual, it can be like a picture. It can be just me verbally explaining how something works. Or it can be like a mathematical formula. There's a lot of different ways to express models in science, and these are just a few of them. Okay, so just remember that. All right, our new vocab for this section, we're going to talk about atoms. We're going to talk about cathode rays. Cathode rays are what's in those old TVs. Maybe you've seen like the big gigantic box TVs that are really heavy. If you like take a magnet to them, it ruins the TV. So those are cathode ray tube TVs. CRT TVs is what they're called. But we're going to talk about what that is. We're going to talk about electrons, protons, neutrons, and then the nucleus of the atom. Here's our main idea. So at the end of the lesson, you should be able to summarize the lesson like so. An atom is made of a nucleus containing protons and neutrons, and then electrons kind of move around the nucleus. You can look at our background here on the slides. So if you see the red and blue, those are protons and neutrons, and then the black dots out here outside of the nucleus orbit, kind of like our solar system. Think of this as like the sun, where the nucleus is, and then think of the electrons as like planets orbiting the nucleus. All right, so that's what we're going to learn. Okay, so let's just jump right in. So we're going to talk about the atom. So the smallest particle of an element that retains the properties of that element is called an atom. And you guys mentioned this a little bit in your bell ringer from yesterday. You said atoms are very, very tiny. They're the smallest parts of matter, right? So you guys already kind of knew that. An atom is as small as you can get. while still retaining the properties of whatever it is you have. So if I have an atom of iron, that's the smallest bit of iron that I can get until if I go any smaller, the properties, I lose those properties that make it iron. Okay? So atoms are the smallest unit of matter that retains the properties. An instrument called the Scanning Tunneling Microscope, or STM for short, it allows you to see individual atoms. And this is technology that's fairly new. Obviously, they didn't have this in the days of Democritus in like 400 BC, and they definitely didn't have this in like the 1800s either with John Dalton. Otherwise, maybe he would have come up with different conclusions. But here's an image of solid nickel. So nickel is a metal, and here's a scanning tunneling or microscope image of solid nickel. Is that what that stands for? I forget. Yeah, scanning tunneling microscope. Okay. And so if you look at nickel, all of these little bumps right there, those are all individual atoms. So we can zoom in with an STM extremely, extremely far. You can see all these little atoms here. So these are what actual individual atoms of nickel look like. Okay. So now that we know what atoms look like, we need to talk about what's inside of an atom. Remember, John Dalton, where we left off yesterday, only knows that atoms are solid spheres, or that's what he thinks. He's not aware of the little particles inside of atoms. And so the first one that was actually discovered was the electron. Okay, and so this was discovered using a cathode ray. Basically, when an electric charge is applied to a cathode ray, a ray of radiation, it's a beam of light. It travels from one end of the ray, or of the tube, to the other. So from the cathode to the anode, and we call that beam of light a cathode ray. Hopefully you'll see an image of it here in just a second. So cathode rays, again, cathode rays are just a beam of light traveling from one end of a tube to another. Cathode rays are a stream of particles, and they carry a negative charge. Basically, they're a stream of electrons that travel from one end of a tube to another whenever you hook up power to it. Okay? Like a battery or something. Alright, the particles carrying a negative charge are known as electrons. So, the experiment that let us discover electrons was a cathode ray, and we were able to observe negatively charged particles, and we call those electrons. Here's a picture of what a typical cathode ray setup looks like. So you've got a long tube, and on either end here, you have a cathode and an anode, and you can hook up a power source to those two ends. So like here's a battery, you hook it up to one end, and then you hook up with the other terminal to the other end, and it creates a flow of electricity. And that flow of electricity, those electrons can travel through the tube, and they generate a beam of light. That beam of light is called a cathode ray. And up here on the top and on the bottom of that cathode ray, you have metal plates. And those metal plates have charges on them. They also have an electrical charge. And so the top one is positive, and the bottom one is negative. So we know that opposite charged things attract, and like charged things tend to repel each other. So that beam of light traveling through the tube will be attracted to the positive plate, since the beam of light itself is negatively charged. So if you imagine a light traveling through this tube would kind of curve upwards towards the positive plate. Alright, that's our setup there. And this figure shows the effect of a magnetic field on a cathode ray. So this is an actual picture of one. You can see if there's no magnet, if there's no positive or negative plate, the beam of light just goes straight through the tube. But once I put a positively charged plate up here, then the beam of light curves upwards towards that positively charged plate, indicating that this beam of light has charge. And whatever charge it has is going to be opposite of the plate that I put above it, if it's attracted to it. So there's what that looks like. Okay, and the guy who made this discovery, the guy who did this experiment and discovered the electron, is named JJ Thomson. So JJ Thomson measured the effects of magnetic and electric fields on the cathode ray to determine the charge to mass ratio. In other words, he wanted to know what charge divided by mass was of a charged particle. And then he compared it to values that were already known at the time. Okay, so I'm not necessarily concerned that you know what exactly his methods were for determining what the charge to mass ratio is. I don't, because it's pretty complicated math. But I do want you to associate JJ Thomson with the cathode ray experiment and with the discovery of the electron. Okay, that's the big thing. So he noticed that the mass of the charged particle was much, much lighter than a hydrogen atom, which the hydrogen atom at the time was the lightest known atom. And it still is. There's not an atom on the periodic table lighter than hydrogen. Okay, but it's actually the electron is much less than hydrogen. And Thomson received the Nobel Prize in 1906 for identifying the first subatomic particle. Subatomic just means it's smaller than an atom. And he identified the first one, called the electron, and he received his Nobel Prize for that in 1906. Okay. Here's a website, and you can go to this on your device, but this website contains an interactive simulation of the cathode ray tube, and it's kind of janky a little bit because it's a subscription-based website, so it might like flash up subscription required while you're playing with it, but you might just need to keep refreshing the page to be able to mess around with it. So let me show you what that looks like real quick. Basically, we have a cathode ray set up here. This is where your electron beam comes from, and it's going to travel down the tube this way. I've got a power source connected to metal plates. You can see the wires connecting to the metal plates, and these will carry a positive or negative charge. I've got a power source connecting to the cathode and the anode so that my beam of electrons can travel through the tube. So if I check that box, the electrons box, you can see the beam of light, and it's going straight, and there's that subscription button. Okay, so my beam of light is going straight because I have no power going to my plates. If I put some power on my plates, watch what happens. This plate becomes positively charged, so my beam of light curves upwards towards that plate because opposite charges attract, and my beam of light is negatively charged. So negatively charged beam of light attracts to the positively charged plate. All right, so you can mess around with that simulation. You can drag this and make the bottom plate positive. You can just uncheck that box and just see where this green dot is. You can mess around with that a little bit. All right. So the next discovery, remember JJ Thomson has discovered the electron, but Robert Millikan was able to tell us a little bit more information about that electron. So in the early 1910s, Robert Millikan uses this oil drop apparatus or setup to determine what the charge of an electron is. So the way this works is you've got like this almost little perfume bottle, and you squeeze that bulb, and it just shoots out little tiny droplets of liquid. And he used oil for this. And so once you eject those little droplets, gravity is going to pull them down, right? Everything that is in the air has gravity acting on it and pulling it down towards the earth. So gravity is going to pull these things down, but if you'll notice, you've got some plates up here at the top, the red, and then here at the bottom, the yellow, that have charges on them. Okay? You have a positively charged red plate and a negatively charged yellow plate. And it's connected to a power source, a battery, some power source that he can change the voltage and make more power or less power run through it with a dial. And whenever he turns the power on, these little droplets are positively charged because whenever you squeeze that bulb, it actually forces electrons to come off of the droplet. So now you have positively charged little droplets falling down, and when you crank the charge up, then the droplets will be attracted to one plate or the other. And, he was able to use this oil drop apparatus and do some complicated math to figure out how many electrons each droplet was losing and the charge of each droplet, and then he was able to determine the charge of a single electron, right? So just using an example, if I know, and these aren't the real numbers, but if I know that each electron has a charge of 3, and this droplet has lost a charge of 6, this droplet has lost a charge of 9, this droplet has lost a charge of 18, then I can assume that I can know the number of electrons that each oil droplet lost, right? So he was able to just use some math, complicated math, and some things that he already knew about charge to come up with the charge of a single electron. That's the idea. Okay? And he learned that charges change in discrete amounts. Discrete just means it changes by the same increment every time. And that increment is 1.602 times 10 to the minus 19 coulombs, which is the unit for charge. But this is a number that's not particularly easy to work with. So we just call the charge of an electron now just 1 minus. We just redefined it as a single unit, and now an electron has a charge of 1 minus. Okay? That just makes life easier for us. So that's why we do it. And then he also was able to figure out that the mass of an electron is this very small mass, 9.1 times 10 to the minus 28 grams. So remember, scientific notation, move that decimal to the left 28 times, and you have 0.27091. Okay? That's how many grams an electron is. It's about 1,840 times smaller than the mass of a hydrogen atom. So a hydrogen atom is the lightest atom, and electrons are 1,840 times lighter than those. Okay? And so he was able to determine the mass because Thomson figured out the charge to mass ratio, and Millikan figured out the charge. So once you know those two things, you can just calculate for the mass. So that's what Millikan did. Okay? So we know that matter is neutral. It has a neutral charge to it. So imagine if matter didn't have a neutral charge. If you had some things that were positive and some things that were negative, what you would end up seeing is things kind of spontaneously attracting to each other and sticking together, and things spontaneously repelling each other and pushing each other apart. But we know that that doesn't happen. Things tend to stay where you put them. Matter is neutral. Okay? Matter is neutral. And so JJ Thomson, since he discovered the electron, he gets to update the model of the atom that Dalton had. Dalton had a solid sphere. JJ Thomson comes up with this plum pudding model. Plum pudding is like a British dessert. It's like a cake with like little fruits stuck in it. Think of like a blueberry muffin or something like that. That's what plum pudding is. Okay, and so his model states that the atom is a uniform, positively charged sphere. So still a sphere, but now it's positively charged, and it contains electrons just kind of randomly placed inside to make the whole thing neutral. So you have a positively charged kind of mush, that's like the cake or the muffin, and then you have electrons just placed in there randomly. Those are kind of like the blueberries, right, of your blueberry muffin. So that is JJ Thomson's updated model after the discovery of the electron. All right, next. I want you to go ahead and take a minute to drag your dot to how you're feeling. You can pause and do this and come back whenever you're finished. If you're good, bring it to the green, really just knowing who discovered the electron and how he did it. And you should know that Millikan also helped with like finding out the mass and the charge of an electron. All right, so bring your dot to wherever you're feeling, and I'll give you some feedback. We can take questions later. Okay? All right, so after the discovery of the electron comes the discovery of the nucleus. So in 1911, a guy by the name of Ernest Rutherford studied how positively charged alpha particles interacted with solid matter. And Ernest Rutherford at the time didn't really even know what alpha particles were. He just knew that if he took solid radium, it was very unstable and it was radioactive, and he knew that it emitted these particles off of it, and he was just going to see what happened if he emitted those particles towards a sheet of gold foil, basically like aluminum foil that's coated in gold, right? And by aiming those particles at a thin sheet of gold foil, what he expected was the paths of those alpha particles to just only be slightly altered by a collision with an electron. So he expected these alpha particles to go through, and if they were to hit an electron, maybe it would change their path a little bit, because he knew alpha particles were positively charged, electrons are negatively charged, they have a little attractive force between them, so he didn't think that they would go straight through, but maybe they would be deflected just a tiny bit. Okay, and although most of the alpha particles went through, a few of them actually bounced back, which is what he didn't expect. And some of them got deflected at very large angles. So you see this one kind of bounced back. You might have also had some kind of go off to the side a little bit at like a 60-degree angle or something. So definitely not what he expected. He expected pretty much all of them to go straight through. So whenever they bounced back, he was like, okay, something's up. This model that we have isn't exactly correct, and I need to refine it. All right, there's a little video here talking about the gold foil experiment. I recommend that you watch it. It's about 5 minutes. This guy does a really good job at explaining what the gold foil experiment was and what Rutherford's conclusions were based on the gold foil experiment. Okay? All right, so in short, Rutherford concluded that atoms are mostly empty space. Remember, Thomson's model was atoms are a solid sphere that's positively charged that has negatively charged electrons just kind of in it. But since the alpha particles pass straight through the atom, Rutherford's like, well, there's no way that it's a solid sphere because then those particles wouldn't pass straight through. He's like, I'm thinking it's mostly empty space, and he was right. So he concluded that because those particles were able to pass straight through the gold foil, the atoms were mostly empty space. He also concluded, since some of those particles bounced back, that almost all of the atom's positive charge and almost all of its mass is contained in a very, very dense region in the center of the atom called the nucleus. So he reasoned that the atom was mostly empty space, and where it was bouncing back, those alpha particles were colliding with the nucleus of the atom. Okay, and he was correct with this conclusion as well. And so he also reasoned that electrons are held within the atom, kind of outside of the nucleus, because they're attracted to the positively charged nucleus. Remember, electrons are negative. The nucleus is positive. Opposite charges attract, so those electrons kind of want to stay close to the nucleus because they're attracted. Okay? I can hear my cat walking up. I'm making sure that he doesn't jump. Okay. So the repulsive force between the positively charged nucleus and the positive alpha particles is what caused those things to be deflected back. So if you have an alpha particle that's going left to right, it hits the nucleus, and boom, positive charge is going to repel. So those particles were just deflected straight back. And that's why he reasoned that the nucleus must be positively charged. Okay. So Rutherford took Thomson's model and refined it to include positively charged particles in the nucleus called protons. Okay. So this is the discovery of our second subatomic particle. Remember, JJ Thomson discovers the electron. He updates Dalton's model. And then Ernest Rutherford discovers the nucleus and the proton, and he updates Thomson's model. Okay? And then the last piece of the puzzle, James Chadwick receives the Nobel Prize in 1935 for discovering the existence of neutrons, which are neutral particles in the nucleus, which account for the rest of an atom's mass. Okay? So some of the mass of an atom is from protons, the rest of it is from neutrons. All right, so after Rutherford discovers the nucleus and protons, James Chadwick comes along and discovers neutrons and completes the model of the atom as we know it today. All right, so just to recap, all atoms now are made up of 3 fundamental subatomic, meaning smaller than an atom, particles. The electron, which was discovered by JJ Thomson, has a negative charge, okay, almost zero mass. The proton, which was discovered by Ernest Rutherford, has a positive charge and accounts for most of the mass or some of the mass of an atom. And then finally the neutron, which was discovered by James Chadwick and has a neutral zero charge and accounts for the rest of the mass of the atom. Okay, so those are your 3 subatomic particles. Those are the 3. We also know that atoms are spherically shaped. So Dalton was right about that piece, at least. And so was JJ Thomson. Atoms are spherically shaped. It's just that most of their makeup is empty space and a nucleus, which Thomson and Dalton did not know. Okay? And again, atoms are mostly empty space, and electrons travel around the nucleus. Think of it like, the planets orbiting the sun in our solar system. The nucleus would be like the sun. The electrons orbiting the nucleus would be like the planets. Okay? So atoms mostly empty space. Electrons travel around the nucleus, held by an attraction to the positively charged nucleus. Electrons are negative. The nucleus is positive, opposites attract, so that's what kind of keeps the electrons there in the atom. Alright, and if we want to know about the chemical behavior of certain elements, certain atoms, then we can explain an atom's chemical behavior by just looking at the atom's electrons. And we're going to do a lot with this, not necessarily in this module, but probably in the next one and the one after that. So just know, chemical behavior, how atoms react with each other, is explained by just looking at the electrons. This table summarizes everything about the particles. The symbol, so if you see E minus, if you see the letter P, or if you see the letter N, these are symbols for electrons, protons, and neutrons. It talks about their location, so protons and neutrons inside the nucleus, electrons surrounding the nucleus, orbiting the nucleus. Okay, it talks about their charge. Electrons are 1 minus, protons are 1 plus, neutrons are 0, neutral. And then finally their mass. So electrons, basically 0. It's 1,840 times lighter than a hydrogen atom. Protons are 1, neutrons are 1. Okay? Alright, so we have another little website with simulations on it. So if you click into the website, you can play around with this. It just shows the gold foil experiment, and you can do it either with JJ Thomson's plum pudding model or with Ernest Rutherford's model. So if you double click into one, here if you push that button, it starts the simulation, and you can see how different alpha particles are deflected. And then if you go back to the Rutherford atom and you push the button, you can see how alpha particles are deflected with the Rutherford model. Right, so some of them hit the nucleus of an atom and they get like super deflected. Like look at this guy over here going to the right. So that one's really deflected. Alright, so you can play around with this and get a feel for what exactly the gold foil experiment looked like and what it told us. I do recommend you play around with that. It's a really good simulation. Okay, we're finished with this lesson. I hope it was helpful. I hope it made sense. We looked at a few discoveries. We looked at the discovery of the electron with JJ Thomson and Robert Millikan, who was able to tell us about the mass and the charge of an electron. We looked at the discovery of the nucleus and the proton with Ernest Rutherford. And then we looked at the discovery of the neutron with James Chadwick. Okay, so answer this question real quick. Pause the video, get your answer in there, come back when you're done. Atoms are mostly blank. Okay, and if you said D, empty space, then great job, you were paying attention, nailed it. Alright, take a look at this question, pause the video, answer it, come back whenever you're finished. So what are the two fundamental subatomic particles found in the nucleus? If you said B, proton and neutron, then you were paying attention, great job. If not, go back and review what the experiments were, what the discoveries were, and maybe play around with this build an atom simulation that we talked a little bit about yesterday. And you can see I can put neutrons in the nucleus and I can put protons in the nucleus, but if I put an electron in the nucleus, it just goes to the outside. Okay, so play around with those things. Simulations are very good. Alrighty. Finally, we got this little video just to put into perspective exactly how small an atom is. It's a really good watch. It's about 5 minutes long. Please watch this video because it will explain exactly how small a single atom is. It's a very good video. And then finally, if you have any questions about today's lesson, go ahead and ask them here. Make sure you complete your exit ticket and make sure you look at the assignment for this section. This assignment is going to be a little bit different. It's not going to be due tomorrow or even the next day. It actually is part of the study guide for this module, so it's going to be due the day before we take the tests, which is still to be determined. We don't know that date yet. But you can go ahead and knock it out whenever you have free time. Just know that it's not due until the day before we end up taking the test for this module. Alright, so I hope this lesson made sense. If it didn't, ask me questions either on here or through Remind or some other method, and I will respond as quickly as possible and as clearly as possible, hopefully. Okay, so with that, I'm going to go ahead and sign off, and I will see you later.